Project Zipper. For a while now, the S3 implementation in RGW has been considered a high-quality S3 implementation. It provides sort of best-in-class capabilities and testing. And so there has been interest in allowing us to provide these features for other storage systems besides just Ceph. So, for example, ISV storage sources like Seagate or Intel, or cloud storage. In addition, we want to provide a flexible API-based framework that allows us to stack filters that can make changes to operations based on interesting scenarios, for example, tiering or caching or something like that. We've actually had requests over the years from people to allow us to allow them to integrate with our S3 protocol stack to provide better S3 for their systems. In addition, we would like to provide the ability for developers to have easy to install local S3 compliant systems for development and local testing of apps. The way we decided to do this was we decided to decouple the protocol layer of RGW from the storage layer of RGW, which we called unzipping it, and then develop an API that cuts the entire way across RGW so that above it is protocol and below it is storage, so that we can add in other plugins that provide storage for the existing protocol systems such as S3. So here's more or less what it looks like. Before, we had a single large system that had all of the protocols and the integration with LibRados API all the way down through Rados to Ceph. What we've done is split it apart so that now you can have several different loadable drivers that provide to the protocol layer the correct amount type of storage, and then each of those can talk to their own storage system. And the obvious example is the RadosStore, which talks to the existing Ceph clusters. The architecture looks like this. At the top, you have your protocols. Below that, we have a core layer that provides operations that are common to all object protocols. Below that, we have our Zipper API, and this provides an abstraction of the various things that object storage would use, such as buckets and objects. The fact that this API cuts entirely across RGW and there's no side channels allows us to actually provide intermediate layers. And they implement the Zipper API both on top and below so that they can perform transformative operations such as caching. And then at the bottom, we have storage layers, which implement the full Zipper API and provide canonical data storage for actual operations. Zipper has been, to a large extent, embraced upstream. The first project was Cortex Motor from Seagate. They had an S3 implementation that was not up to their standards, and so they looked around and found Zipper and decided that they would attempt to implement a driver for the Zipper API, which they did in a couple of months. And it is now in their upstream, and it is in our upstream, and it's been pretty successful. The second one was Deos from Intel. They have a memory-based storage system and needed an S3 implementation to live in front of that. And again, they implemented a Zipper driver in fairly short order. The third big project is Aquarium from SUSE. They were providing a hybrid file/database standalone driver. The goal is to provide a high-performance single node S3 implementation that can be used in situations that require single node, such as Extreme Edge. So the Zipper API, at its base level, we provide a set of pure virtual base classes. And these cover the various concepts needed to implement operations on an object store. The most important of these base classes is the store. It is an entry point for a storage abstraction or a filter. There's a single instance of it for each running RGW that provides access to the other classes and allows the proper stacking. There's a set of primary abstractions that we use for getting stuff done, such as users and buckets and objects and multi-part upload. There's a set of helper classes that let them help the main classes provide their work, such as a serializer or a writer, which is an asynchronous writing class. We provide lifecycle implementations, and we provide cluster layouts, such as zones and zone groups. And then RGW has the ability to embed Lua scripts, and so we provide a Lua manager that allows you to store and retrieve Lua scripts in your store. There are two implementation. Stores sit at the bottom of a stack, and they implement the entire API, and they provide canonical storage for reading and writing data and metadata. The base implementation is in RGW Sal Store, and it provides the keys and the key data for each type so that all stores will have the same key data. A filter is an implementation of the API that lives in the middle and performs a transformation on an operation as it passes down the stack. A filter does not need to implement the entire API because we provide a base implementation that is passed through so that any portions of the API you do not override just get passed through for you. A filter will optionally make a transformation and then pass that down the stack. And then the results from lower in the stack get passed back up and again, optionally perform a transformation. At the top level, we have the Zipper implementation is in sal.hncc. It's the pure virtual API. And it also provides a manager that allows the loading and stacking of stores and filters. And also, RGW sal.h contains the canonical documentation in the form of Doxygen for the API. We also have the implementations of the base classes for stores and filters, and those live in Sal Store and Sal Filter, respectively. Implementations of stores or filters live in Sal implementation. So Sal RADOS is the RadosStore implementation, and Sal D4N is the D4N filter implementation. And there's a store directory that contains an implementation directory for each store or filter that has the detailed implementations of that store or filter. Each store or filter is a loadable module. The config for it lives in a JSON document, which lives in a config store that is cluster-wide, so that every RGW in the cluster has access to the same information about stacking filters and stores. At config load time, the config store manager determines which stores and filters need to be loaded and loads the associated plugin and sets up the stack of filters and stores correctly. Plugins can be created in tree or out of tree, and only the loadable library needs to be available at runtime. The loadable plugin work is not fully complete, but it is almost complete, and that should be finished within the next month or so. I would like to go a little bit through code. So this is the, as an example, this is the pure virtual base class for an object. You can see it contains some subclasses that help, for example, reading and deleting. It contains operations such as copying. It contains accessors, for example, to tell if something is compressed or change compression. There are methods for accessing attributes, transitions to and from the cloud, placement rules, and so on. Ways of interacting with the bucket, which owns this particular, contains this particular object, and then OMAP and such things as that. The store object provides the base class for a store implementation of an object, and it contains the key data for this particular object, which in this case is an RGW obj state. It also contains a pointer to the bucket containing this object and has a cache of the attributes for this object. This allows every store to have the same key data and to not have to implement the key data on their own, which allows for consistency across stores. Other than that, this only provides access to the key data that it stores and does not override any other methods. So a store would inherit a given store's object, for example, a RADOS object, will inherit from this class. And then in a filter, the filter object contains only a pointer to the bucket that contains the object at this level, so the same filter object, the same filter bucket at the same filter level, and it contains the next layer, the object in the next layer in the stack. So if there is another filter below this object, then next will point to that filter. If there is a store below this object, then next will point to that store. And all the implementations of all of the methods, as you can see here, just pass through to the next layer down. This means that any filter which will inherit from this, such as D4N filter, can override only the methods and objects and methods and classes that they care about. All the rest of them will fall back on this default implementation, which passes through down to the next layer. That's the basics of Zipper. Are there any questions? Question is there any plans on having some form of gRPC backend where Zipper would call services? It can deal with the operations, and they would decouple it from C++. Currently, there is no plans to decouple from C++. There is a plan to write a LuaFilter, which will be an implementation of the filter layer in Lua, which will allow scripting of filters for rapid development. But there is currently no plans to decouple this from C++, which doesn't mean it won't happen. It just means that we haven't planned to do it yet. Other questions? All right, well, if there's no other questions, then thank you for coming. And if you do have offline questions, feel free to email me or hit me up on Google Chat, and I will be happy to answer them. Thank you.